So, welcome back. Now, this is the part two. So, now we'll just jump on to conservation laws. So, conservation laws technically determine what equations you're gonna enforce into a control volume. So, I'll just write it conservational conservation laws. So, the main transport equation. So, if there's anyone who knows the transport equation, or you learn it in transport phenomenon or fluid dynamics, that's the transport equation. So, the general transport equation goes as such. So, you have your dou and rho phi by dou t plus del times of rho v and phi again is equals to your del times of rho, not rho, you will have tau over here. If I'm not wrong, tau del of phi plus your s of phi. So what each of them represent is, so your this term is technically your rate of change of phi within the fluid and element. So rate of change of phi of the fluid element. So the density here, rho, ensures that the property of the fluid is taken into care. Then yeah, um, this term, this represents the net rate of flow. So net rate of flow of phi, so of the parameter phi, out of the fluid element, out of the fluid element. So yeah, so this term. So if I have a phase, it technically tells me the rate of flow of the parameter phi within each of the fluid elements. So if this is one of my fluid element, it technically tells me the flux, right? So it's like a flux term. Then you have this term. This is rate of increase, rate of increase of phi due to diffusion. So this term is famously that you call the diffusion term. So diffusion through each elements. So this is the diffusion term, and then this is just an term of source term, in the sense that it depends on the source. So if there's any change in a rate of change in phi due to source. So a source of fluid or source of whichever element you are considering for the CFD simulation. So based on that, if there's any change in phi or the element, or the parameter that you are trying to calculate, then that is covered with S of phi that we are considering. So this is your general um, transport equation. So you have one term here, you have the second term, you have third term, and you have fourth term. Now the good thing about this transport equation is that if you remember this equation, right, this transport equation, you can now generate or um, derive other equations from this. So for if your phi equals to 1, so just imagine if you put phi equals to 1, so you get d rho by dt. So d rho by dt plus, here instead of phi you put 1, so you get uh, del rho v is equals to, you put 1, so del of del, again this is 1, so del of tau of del will become 0, and this we are just ignoring the source term because we are taking it as 1, so it's a constant, so you won't have any change. So this will be equals to 0. Now this is your continuity equation. Now if you put phi, if phi equals to v, right, I'll just go down. So if phi is, okay, bit up, such that the equation is seen. So So the equation is seen. I'll just write it here. So now if your phi is v, so d rho v by dt plus your del rho v v plus is equals to del u del u minus, or sorry, the plus the source term, that is your s of your v, the source term due to v. So this is what you call your momentum equation. Momentum equation. So your momentum equation is, when you put it in the transport equation, is generally what you call the generalized Navier-Stokes. So this is your generalized Navier-Stokes equation, right? So this is one of the most these two equations are the most important equations for CFD. So now again, it's not over here yet. So now if you replace it with, if your phi is equals to, zoom in a bit, if your phi is equals to C, that is a concentration of any chemical or concentration of any flow, then you get your transport equation. Transport or species equation. Since I've used transport up, I'll just not use transport over here. So this is what you call your species equation. So if you have opened ANSYS Fluent or any other software for CFD before, you might have seen this term, right? Species equation. So species equations is used for chemicals, or if you have any chemical exchange. So for example, again, I'll just go back to the pen. So yeah, this is called species equation. So where do you use this? Just assume if I have a combustion engine, I mean, I'll just assume that you are getting fuel from here and fuel from here, and technically you have injectors from here. So you are injecting fuel um, and oxidizer. So you have the propellant and oxidizer, and then from here it goes into a nozzle. So now flow from here is dispersed over here, right? So whatever happens here, right? It's a part of species in the sense that you have uh, you have a propellant plus you have oxygen O2, right, as oxidizer. So now in order to determine the flow, you need to know the concentrations and how these chemicals behave inside, right? So this is taken care by your species, right? And the C over here represents concentrations. So this is why you use species equations. So this is very important if you are doing something related to rocketry or propulsion systems in general, or if you are going with CFD of battery packs, etc. So yes, that is it for the conservation laws. So now we'll jump on to one of the most important topics in CFD, that is your solvers. Solvers, right? So if you open a workbench, or sorry, ANSYS Fluent, you see two options. One is pressure-based solver, pressure-based, and the other one is density-based. Now these two are extremely important types of solvers, and none of them can be neglected because the use case for both are different. So here what happens in the pressure based equation is, just understand carefully. So here your velocity is calculated from momentum equation, right? Then density is um, rho. Density comes from your equation of state. Equation of state. So if you don't know what equation of state means, it's technically your PV is equals to nRT, which you can write it as P is equals to rho RT, right? So you know the value of momentum, sorry, V, then you plug it into continuity equations, you get value of P. sorry, continuity and momentum equation, you get value of P. You replace it in the state equation, you get your rho. So this is how you get density in your pressure based equations. So once that is done, so your pressure comes from uh, equations of continuity and motion, right? So P comes from equations of momentum and equation of continuity, that is the continuity equation. So this is where your P comes from. So this is your pressure based equation. We will check in detail when I segregate pressure based as well. So how exactly that works. And in density based, it's just almost the same, that your V comes from momentum equation. But here now your rho density comes from continuity equation and not continuity equation and not equation of state. Now there's a very logical theory for this, a logical reason for it. So your pressure based is usually used for conditions where your Mach is less than zero point 0.3. So what does this condition mean? It means that your region of solving or your domain of solving, region of flow, is incompressible. Incompressible, right? So what does this mean? If your region of flow is incompressible, or if your flow is incompressible, it means that your density is almost constant. Your rho is constant, almost constant. So you can take it from equation of state, right? Because here only P is changing, RT and rho is constant. But if you are going to compressible flows, so compressible flow, generally you take it as m greater than zero point 0.3. So m here refers to your Mach number, that is your speed of sound divided by speed of uh, whatever material that your uh, fluid is passing through. Uh, so yes, that is your Mach number. And next, so m is greater than zero point 0.3. So this is when you use your density base, because here in compressible flow, your density changes your density changes at each point. At each point. And I'll just write this in case anyone doesn't know. So this is your velocity of sound divided by velocity of the object that you are comparing it with. So, and if I'm taking a rocket, then velocity of the rocket uh, will come here. Okay, my bad. I is to the power minus one. So it's v of object divided by v of sound. My bad on that. So yeah, that is your Mach number. I'll just erase the other one. So yeah, so your velocity of sound, object divided by velocity of sound is your Mach number. And if it is greater than 0.3, then it means it's under the compressible regime. And if it is less than 0.3, it's mostly under the incompressible regime. And that is where you get a differentiation between these solvers or the methods used, right? So if I want to find, I don't know, let's say flow in a pipe, I'll directly use a pressure based flow, just because it's incompressible, right? Your water through a pipe doesn't go above zero point 0.3 Mach. It's just impractical. And density, I would use, suppose, flow through a nozzle. So when you know your density is changing, you use the density based equation. So if that's simple enough now to understand, let's move on. So now moving on, we'll directly get into your pressure based in detail thoda. So your pressure based equations, pressure based your pressure based equations can be made into segregated and coupled. That's your coupled equation. So now it's important to understand the differences. So you're going into a bit deep of CFD now. So what segregated method does is, I'll go in step. So first it solves your momentum equations. So let's say number one solves momentum equation, right? So then you go to your method where, sorry, part where you solve for pressure correction, pressure correction. Then you go and update V, P, and flux. Then you solve, just go down, you solve the other energy models, solve for energy species. We have species and then turbulence, and then you check if it is converged or not. Check if the solutions are converged. If it is not converged, then you go back up, and before solving the momentum again, you update values. So this is like the general way of how it's done. Now I know this might be kind of confusing of what is going on. So now the point is you have multiple methods to do this. So I'll be covering this in detail further when I'm talking about each of this. But for now, let's say that one of the method is simple, right? SIMPLE. So I'll just tell you how it works in general right now, so you can just understand how it moves on. So you take a value of p, you assume a value of p, that is p star. You put it in momentum equation, right? Now with this you get values of v, u, and w. So v star, u star, w star. So these stars means it's just assumptions, right? So you assume p star value. So the solver first assumes a value of pressure, then it puts it into the momentum equations, and using the momentum equation you can find velocities. So momentum equation is not one equation, you have x, y, and z momentum equations, and with p star you find v star, u star, and w star. So hope you know that v is in the y direction, u is the velocity in x direction, and w is the velocity in z direction. So with this you find it, then you put these values in continuity equation. Now what values? I'm talking about the velocity values, because your pressure is no way related in any form in the continuity equation. There is no pressure term in continuity equation. So you put velocities in the continuity equation, and now whatever errors that you get, so you'll get some errors, so that is now you will find some correction terms. So now using the velocity, so you get some other velocities, you check if it is not satisfied. So when you put these values in the continuity equation, you're not finding anything in the continuity equation, right? So when you're putting it in the continuity equation, you're checking if it is satisfied. So you're checking if the mass balance is fine, right? So as I told, the continuity equation, that is your d rho by dt plus your uh, del times of rho into v is equals to 0. So you put the values of v, I mean, you know rho, so you put the value of v and you check if it is 0. If it's not 0, you have a correction term. So your pressure correction term, you find some pressure correction term, then you find velocity correction terms, right? So these correction terms are calculated by the uh, solver using some internal methods, and then you update the values, update values. So how the values are updated? It's just simple. So you your p new is equals to your p star plus p dash, right? So your original assumption plus your this correction value. Now with this you put back into the, so your new term p new goes instead of your p star, and this whole process continues until your values converge. So when will your values converge? Is technically when your continuity equation is nearly getting solved. That means when you substitute v, uh, okay, now zooming in, when you substitute v, it, sorry, not v, your v star. When you substitute your v star, it should be equals to 0. That is when your solution is converged, right? So this is your segregated. So why is it called segregated? Is because it goes sequentially, in the sense that first this takes place, then this equation, this step takes place, then this, then this, then this, and then this. So this iteration keeps on happening, and each step of this iteration happens one after the other. That's why you have it. That's why it's called. That's, I'm sorry. That's why it's called sequential, right? Now moving on to the coupled form. So coupled. So we checked what segregated was. So now checking what um, your coupled is. So this is simple as the name suggests itself. So I'll just zoom in a bit. So what it does is you solve for P V W I mean, sorry, P V W U all together, all together. Then, I mean, this is, so you will solve the momentum and continuity continuity equations. You solve all these simultaneously. So you solve these equations, all these equations simultaneously, and you keep getting the correction terms. You get correction terms simultaneously, and then you energy, solve for energy and turbulence, etc., as we did before. So this is always usually the last step, and then you check if it is converged. If not converged, go up and update the values and restart. So you go for the next one, that is your pi plus 1, ui plus 1, wi plus 1, and ui plus 1, where I is the which iteration it is on, iteration count. So yeah, this is your coupled. So in a gist, I'll just explain it once again, because of course my handwriting is it's bad, so I'll just go on. So you have your segregated and your coupled uh, under your pressure based equations. So under segregated, what it does is that first it solves the momentum equation. So it assumes, like, let's say a value of p, so we call it p star. Then you replace it in the momentum equation. You get values for v, u, and w, that is your v star, u star, and w dash. The star is just demarcating that it is an um, assumed value. Then you put it in the continuity equation. You check how far off it is on solving that continuity equation. Based on that, you uh, you have correction term, that is dash, that is p dash, v dash, u dash, w dash. You update the values. How the values are updated is using this, your p nu is equals to p star, that's your previous assumption, plus the correction term, that is your new value, and now again this whole cycle repeats. So that's exactly what is written here. So you do this until the values are converged. The values are converged when your continuity equation is satisfied. So in coupled, what it does is just, so this happens, so the segregated one happens sequentially. That's why it's called segregated. So it's slower. Your coupled is where you are solving for p, v, w, u, and any parameters. So these parameters, it's not necessary that it's only these, that is your p, u, v, w, can be any other parameters. So it, in coupled, you solve all these equations, that is your momentum and continuity together, and you solve for p, v, w, and u simultaneously. So then based on the errors, again you come up with a correction term, and then you solve the for energy and turbulence at the end. Check if it is values have converged, and if it is not converged, you again update values, and the cycle goes on, right? So a difference would be easily noticeable, that this is slower because computational, more computational time. Over here it's faster because you're solving all together, right? So here you solve it through matrix and linear algebra. So you have your P, V, U, and W, and so you have multiple iterations I1, I2, I1, I1, I1. Then you have 2, 2, 2, 2, and then this goes on, right? So you solve all of them. So this is how you solve for the values of P, V, U, W all at once. And yeah, this is the basic segregation for the solvers. So you have pressure based and density based, and under pressure based you have segregated and coupled base. Now why we are not talking for the density based is that density based directly uh, I'm sorry, yeah, density based equation. Just zoom in. Yeah. Density based solver directly uses coupled. Okay, so just keep this in mind. So it directly simultaneously solves your values of P, U, V, W, because as I mentioned up, you can see what does it do. It calculates V, then takes it from continuity equation. So you solve all of the values simultaneously for the system using coupled. So there is no segregated way for density. You're just together solving for every value, every parameter that you need in coupled. Okay. So I hope that is clear. So now next, from the next topic, it would be meshing. So meshing is like one of the most important. If you have to choose like 2 3 topics out of CFD which are the most important, meshing is definitely top on that. So meshing, again I'll cover it in the next part. So till then, yeah.